Hello and welcome. In this video, we're going to take a look at a very convenient formula for turning a function into a power series. And it's called the Taylor series with this one specific case called the Maclaurin series. Now the goal here is to take whatever function that we're given, and it can be a pretty complicated function, let's say, and turn it into a power series, which really just makes it a polynomial. A polynomial with infinite degree perhaps, but still something much easier to work with, easier to integrate, and easier to differentiate. So let's start off by supposing that whatever function we're given, f of x, can be represented as a power series centered at x equals to a. Here's that general form. F of x is going to equal some series of Cn, our coefficient, times x minus a to the power n from n equals 0 to infinity. To be able to conveniently come up with this power series, let's see if we can come up with a formula for the coefficients in general. Now there's a nice convenient way to at least solve for the first coefficient, c0. If we first start out by expanding the series into its first several terms, c0 plus c1 times x minus a plus c2 times x minus a squared and so on, you can see that if we plug in x equals a and we substitute a in for all of these values of x, that most of these terms are going to be ending up as 0. We'll just have f of a on the left-hand side equal to c0 on the right-hand side. And that already gives us our first coefficient. c0 is simply equal to the value of f evaluated at x equal a. Okay, well, how are we going to find the next coefficient, c1? Well, the nice thing about a power series is that since it's a polynomial, if we take its derivative, then that first coefficient, c0, using the constant function rule, has a derivative equal to 0. And then using the power rule on each of the subsequent terms, we're going to get c1 plus c2 times 2x minus a plus c3 times 3x minus a squared and so on. All of those nice power rules, we'll see the power drops by 1 and we multiply the coefficient by the old power. Well, now that we've done that derivative, again, if we just plug in x equal to a on left and right hand sides of that equation, we'll see that c1 must be equal to f prime of a. And that gets us our second coefficient. Now let's continue this process and you'll see a nice little pattern here. With the second derivative of our power series expansion, the derivative of c1 is 0, and then we have the derivative of 2c2 times x minus a, which is 2c2. And then be careful with these power rules. You see that we already have 3c3 times x minus a squared. When we apply the power rule again, we're going to get 3 times 2. That'll be 6c3 x minus a, and so on. But to try to get a better pattern, rather than writing 6, let's just keep that as 3 times 2 for a moment. And you'll see this nth term in general, take its derivative once, we'll get n as multiplying the coefficient, and the new power will be n minus 1. And if we take another derivative, we're going to get n times n minus 1, and the new power is going to be n minus 2. So be careful. We'll have to see where this pattern goes. Now, again, plugging in x equal to a, we get f double prime of a is equal to 2 times c2. Or in other words, if we want to solve for c2, our third coefficient, c2, is equal to the value of f double prime at a over 2. All right, one more time here. Let's do another derivative and see what it looks like when we're looking at f triple prime. So now this time, that 2c2 has a derivative equal to 0. And our first non-zero term is going to be 3 times 2, c3. And I'm skipping a lot of terms here. Once again, if we plug in x equal to a, we get f triple prime of a is equal to 3 times 2 times c3. And this time c3 is actually equal to f triple prime of a divided by 3 times 2. Now, let's stop doing this one derivative at a time and let's take a look at what the power rule is doing to the coefficients of each of these terms. Every time that we take a derivative, we're bringing the power to the front, multiplying by the coefficient, and dropping the power by 1. So the nth term of this power series, by the time we've done multiple derivatives, you can see we have n times n minus 1 times n minus 2 times n minus 3 and so on. And that's exactly what happens when we look at n factorial. If we have taken the nth derivative, then we can solve for Cn. And that will be equal to the nth derivative of f evaluated at a And then we're dividing by n times n minus 1 times n minus 2 times n minus 3 all the way down to 1, which is equal to n factorial. That formula there gives us the value of the coefficients of the power series we're looking for. And this is what we call a Taylor series expansion for a function. After going through that process and figuring out what the coefficients need to be, we say that the Taylor series of this function f at a, because it's currently centered at x equals a, is the series from n equals 0 to infinity of the nth derivative of f evaluated at a divided by n factorial, those are our coefficients, times our x minus a to the n. And that is just generally the form of a power series centered at a. Now, in the special case where a is equal to 0, we actually call this the Maclaurin series. The Maclaurin series looks identical, it's just that all of the a's here are replaced with zeros. So the Maclaurin series, you could actually just say, is a Taylor series of f at 0. Now, if you really wanted to take a look at what these look like when they expand out, the Taylor series expansion would be f of a plus f prime of a times x minus a plus f double prime a over 2 factorial times x minus a squared plus f triple prime of a over 3 factorial times x minus a cubed, and so on. And here you can see that the first two terms are actually over 0 factorial and over 1 factorial, but 0 factorial and 1 factorial both equal 1 by definition. The Maclaurin series, similarly, if we expand that out, is just f of 0 plus f prime of 0 times x plus f double prime of 0 over 2 factorial x squared, and so on. Now, it's because of this nice formula that we can take some common functions that we think of as being transcendental functions. They are not polynomials, they're not algebraic, but we can express them as algebraic functions. Things like sine and cosine and e to the x, or maybe even certain logarithmic functions can be expressed as polynomials. And we'll take a look at those radius of convergence and see if they do a good job of approximating that function, whether or not they converge to that function over all real numbers, or perhaps only over a finite radius. Let's start off with a pretty classic example of finding the Taylor series expansion of the function e to the power x. And let's start off by looking at the Taylor series centered at a equals 0. So it's also just known as the Maclaurin series for the function e to the x. All right, well, we need to come up with the coefficients, and we can do that one at a time, but let's see if we can also come up with a formula for the coefficients in general for this function e to the x. Remember that the nth coefficient of the Maclaurin series, or Taylor series at 0, is the nth derivative of the function evaluated at 0 over n factorial. So let's maybe make a little table here of the various different derivatives of e to the x evaluated at 0. The nice thing with e to the x is that all of the derivatives are the same. So in this table, we'll start at n equal to 0, and the 0th derivative doesn't make a lot of sense. Essentially, that is just f of x. That's the function that we're given, and we're not taking a derivative at all. If we plug 0 into that, then f of 0 is equal to 1. Okay, well, let's take a look at the first derivative when n equals to 1. And we know that the first derivative of e to the x is e to the x, and we'll evaluate that at 0. And of course, f prime of 0 is also equal to 1. It's a pretty easy pattern, but we'll want to set up this table in general. So let's just try one more row. Second derivative, of course, again, is e to the x, and f double prime of 0, again, of course, equals 1. So in general, for any nth derivative, the nth derivative of x is equal to e to the x, and the nth derivative of e to the x evaluated at 0 is always equal to 1. So using the formula for the nth coefficient of a Taylor series centered at 0, or a Maclaurin series, the nth derivative evaluated at 0 over n factorial is always just going to equal 1 over n factorial. That tells us that e to the x can be represented as the power series from n equals to 0 to infinity of 1 over n factorial times x to the n. If we wanted to expand out the first few terms, that means that e to the x is equal to 1 plus 1 over 1 factorial times x to the 1, well, that's just x, plus 1 over 2 factorial x squared, well, that's just 1/2 x squared, plus 1 over 3 factorial x cubed, that's 1 over 6, or 1 over 3 factorial, x cubed, and so on. We've taken some sort of transcendental function that is not algebraic, and we've expressed that as a polynomial now. Now, that's not to say that they are necessarily equal to each other. That just means that hopefully this polynomial converges to e to the x. But let's see if it converges for all real numbers for only a single point or over a finite radius. We'll need to use the ratio test for that. To set up the ratio test, we're going to be taking the limit as n goes to infinity of the absolute value of the ratio an plus 1 over an. Now here, an is 1 over n factorial x to the n, or we could rewrite that as x to the n over n factorial. And because that's a fraction, it may be a little better to write the ratio test using an plus 1 times the reciprocal 1 over a to the n. Replacing the n's with n plus 1, that gives x to the n plus 1 over n plus 1 factorial, and we'll multiply by the reciprocal, n factorial over x to the n. Let's see if we can simplify that, maybe get rid of that absolute value if possible, and find out whether this ratio is less than 1, greater than 1, or equal to 1. Now, we've used this ratio test a few times in previous videos, so you'll probably be familiar with this strategy of coming up with common factors and separating the fraction out and applying the absolute value to each of those separate fractional expressions. And the first one is only involving n, and since n is greater than or equal to 0, this is always positive, and we'll get rid of that absolute value. And we can split that n plus 1 factorial up in the denominator. That gives us n factorial over n plus 1 times n factorial, and we can cancel n factorials out and leave a 1 in the numerator. And we have x to the n plus 1 over x to the n, and using just basic exponents, that is equal to x. But we'll have to keep the absolute value on x because x could be potentially any real number. This, however, is just a constant with respect to n. We can move that out front, and we need to only take the limit as n goes to infinity of 1 over n plus 1. And that is equal to 0. So by the ratio test, no matter what x is, this ratio is always less than 1, and therefore it is absolutely convergent for all real numbers by the ratio test. If we wish to state the interval of convergence, then all real numbers can be represented as the interval from negative infinity to infinity. We always use round brackets for infinity. And the radius of convergence would be r equals infinity. So this is pretty big as far as the conclusion goes. This says that e to the x is exactly equal to 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and so on from n equals 0 to infinity. They are exactly equal to each other over all real numbers. That means that we can actually express e to the x as just an infinite degree polynomial. Maybe let's take a look at Maple here, and we'll see how, as we include more and more powers in our power series, that the graph of this polynomial and the graph of e to the x will look identical to each other over all real numbers. All right, here in Maple, I'm using a package, Student Calculus 1, because it has some really convenient tools for animating Taylor approximations. And here's our function, e to the x. We'll just define that first. And when we use the basic Taylor command, you can see it is giving us the same Taylor series, 1 plus x plus 1 over 2 factorial, x squared, plus 1 over 3 factorial, which is 6, x cubed, plus 1 over 4 factorial, x to the 4, and so on. You can see that 0 factorial, 1 factorial, 2 factorial, 3, 4, and 5 factorial, they're growing very quickly. And this notation, big O notation, means that the remaining terms are on an order of at least x to the 6. We can even include more terms here if we like. If we choose to have all the way up to x to the 9, these are the first 10 terms, and it'll hide all terms of higher order x to the 10 and up. And you can see, now we've got 6 factorial, 7 factorial, 8 factorial, and 9 factorial. Now, let's start by plotting some of these Taylor series. And here is the very first term of the Taylor series. The first term is simply just equal to 1. And the red graph here is e to the x. Well, they don't really look very much alike until we start including more terms of our Taylor series. Here's the first two terms, 1 plus x. Well, at least you can see that now this blue curve is actually tangent to e to the x. And then we'll try the first 3 terms. And there's our parabola, 1 plus x plus 1 half x squared. And now they're starting to look very similar. It's converging. It's not just converging at a point, though. It seems to be converging over a little wider interval. And we'll go ahead and try all the way up to our x cubed term. And now we've got a pretty nice area of convergence there. Now, rather than me editing this and trying to plot each individually, let's get rid of that and take a look at this Taylor approximation command with the degrees from 1 up to 10 with an animation as its output. And from here, you can see that the first polynomial we have, degree 1, that's going to be 1 plus x. The next frame in this animation is going to have a degree 2, and that's 1 plus x plus 1/2 x squared. The next frame is a cubic, and a quartic, and a quintic, and a sextic, and we'll just keep going ahead, and you can see that the more terms we include, the higher the degree of the polynomial that we are creating, the closer that that blue curve is to following the actual exponential function. So there's that animation. Pretty quick. Maybe we'll slow that down a little bit here, and we'll just have only maybe a couple frames a second. And you can just see that as we include more terms, the blue curve approximates e to the x. We can even zoom out a little farther. Here's -10 to +10. And here's that animation again. You can see it's getting closer and closer over a wider and wider interval. Eventually, we will need to include more terms to see that proper convergence. So here's the first 20. And there we go. We've pretty much converged over the entire plotting interval from -10 to 10. Let's take a look at some other examples of turning these transcendental functions, non-algebraic functions, into Taylor series. Let's repeat this process with a trigonometric function, f of x equals cosine x. Again, let's center this at a equals 0. This can either be referred to as a Taylor series centered at 0 or a Maclaurin series. This time around, it's going to be very useful to set up that table of the derivatives of cosine x because they're not always the same like they are with e to the x. So we'll make one column for n, and we'll take a look at the nth derivative, and we'll evaluate them all at 0, which is our value of a in this case. Now, luckily, the derivatives here do follow a nice pattern, starting with the function itself, cosine x, and then the next derivative, negative sine x, the second derivative, negative cosine x, the third derivative, sine x, and the fourth derivative, we're back to where we started. And then it repeats its process again afterwards. Now, we're going to evaluate each of these at 0, because that is our value of a in this case. Cosine of 0 is equal to 1. Negative sine of 0 is equal to 0. Negative cosine of 0 is equal to -1. Sine of 0 is 0. And then we're back to cosine of 0, which is 1. You can see this nice pattern that all of the odd coefficients are 0. Now, remembering the formula for the Maclaurin series, it is the nth derivative of f evaluated at 0 over n factorial times x to the n. So this table here is just giving us the values of the nth derivative of f evaluated at 0. We still need to take these values, divide by n factorial, and multiply by powers of x. So starting with n equal to 0, the nth derivative at 0 is equal to 1. 1 over 0 factorial times x to the 0. And when n equals 1, we have 0 over 1 factorial x to the power 1. When n equals 2, we have -1 over 2 factorial x squared. When n equals 3, we have 0 over 3 factorial x cubed. When n equals 4, we're back to being positive 1 over 4 factorial x to the 4, and so on. All of the odd terms have coefficients equal to 0, so this simplifies just down to 1 minus x squared over 2 factorial plus x to the 4 over 4 factorial, and we can continue that pattern on. Now let's see if we can take this particular pattern with powers of x that are always even and denominators that are just simply the even factorials and come up with a better formula for cosine x. What we'll do is once we've written out the several terms of this series, let's renumber them, starting at n equals 0, n equals 1, n equals 2, n equals 3, and so on. Now, can we write that in summation notation with these indices of n? Well, the first thing you'll notice is that the power on x is always equal to 2 times n. So we can write that part out first. Every one of these terms is going to have x to the power 2n in it. Similarly, in the denominator, it's always 2n factorial. The only part that we're missing is the alternating signs, positive, negative, positive. If we want the first term to be positive, then for our power of -1, we should choose n, since when n equals 0, that will give us +1, and when n equals 1, we'll get -1, and all even terms will be positive, and all odd terms will be negative. This will allow us to actually write cosine x in a nice compact summation notation form. There we go. Cosine x can be written as the power series n equals 0 to infinity of -1 to the n times x to the 2n all over 2n factorial, and the parentheses around that 2n is important, so it's not just 2 times n factorial, it is 2 times n all factorial. Now, what about the radius of convergence? Let's see whether or not this particular power series representation will approximate cosine x over a finite radius, an infinite radius, or only at a single point. Once again, we'll have to use the ratio test. Starting off with that limit as n goes to infinity of the absolute value of an plus 1 over an. We'll multiply an plus 1 by the reciprocal of 1 over an. That gives us -1 to the n plus 1 times x to the 2 times n plus 1. Be careful with these brackets. In the denominator, that is 2 times n plus 1, all factorial, and then multiply by the reciprocal of an again. Now, very conveniently, any factors of -1 when we take the absolute value are going to be equal to 1. So we can ignore those -1s because the absolute value of those is simply 1. Splitting up the other factors, we have one fraction of 2n factorial over 2n plus 2 factorial, and we have powers of x, x to the power 2n plus 2 over x to the 2n. Now, when we are canceling some powers, we can also take a look at these absolute values while we're at it. And we know that since n is greater than or equal to 0, that everything in this first term is going to be positive anyways. And we can split up that bottom factor. Counting downwards, 2n plus 2, 2n plus 1, and then we have 2n factorial. That's going to allow us to cancel the 2n factorials and leave a 1 in the numerator. Now, simplifying powers of x, x to the 2n plus 2 over x to the 2n, that just gives us x squared, and x squared is always positive, so we can drop the absolute value sign. X squared is constant with respect to n, so that can be moved out front of the limit, and we have the limit as n goes to infinity of 1 over 2n plus 2 times 2n plus 1, and that is equal to 0. So regardless of what x is, since x is any real number, this limit always evaluates to 0, and therefore it is convergent for all real numbers. So much like our power series representation of e to the x, we can say that the interval of convergence here is all real numbers, and the radius of convergence is infinite. Once again, let's take a look at Maple here and see how this particularly strange looking polynomial actually converges to the shape of cosine x. All right, with a few changes to the code here, I've got the function now as cosine of x. And then here with the Taylor series command, Taylor, we can take a look at the Taylor series all the way up to any orders of x less than 10. So this is going to be only the even powers. We have 1. Our second non-zero term is -1/2 x squared. Our third non-zero term is 1 over 4 factorial x to the 4. Our next non-zero term, 1 over 6 factorial x to the 6. And you get the idea. This is actually fairly similar in some ways to the exponential function's polynomial, but it only has even terms and they have alternating signs. Now, unfortunately, the Taylor approximation command that I was using for animations doesn't really allow you to customize the vertical axis, and it's pretty hard to compare the graph of cosine x and these polynomials when cosine x only goes from -1 to +1 on the vertical axis. So we'll have to do it manually. Here you can see, I'll just zoom in a little bit, is the graph of our function cosine x and the very first non-zero term, which is just 1. Well, the graph of y equals 1 is pretty terrible. So let's go and try the first 3 terms. All right, the first 3 terms, of course, one of those is 0. This is just going up 1 plus 0 minus 1/2 x squared, and we get that parabola. Okay, well, let's include a couple more terms. Again, one of those is going to be 0. This is 1 minus 1/2 x squared plus 1/24 x to the 4. You can see they got that quartic. And it's starting to really follow the same curve as cosine. We'll include the next non-zero term and the next non-zero term. And we're animating this by hand here. You get the idea though. You can see that the more non-zero terms we include, we start to really get really close to that cosine graph. We can even zoom out as far as we like here. And you can see we're not very close to approximating cosine x, but if we were to include maybe twice as many terms roughly, we're starting to get a wider and wider range of convergence. And you can see we're getting really close. I've included 50 non-zero terms. The oscillations are so wild as we get farther away that Maple has a tough time graphing them. But we've converged to cosine from about, I guess, negative 6 pi to positive 6 pi-ish. All right, well, now that we've taken a look at the Maclaurin series for e to the x and cosine x, you can probably imagine that the Maclaurin series for sine x is also very similar. You should try it out. What you're going to find is you'll only get the odd terms. Now, if you think about it, that shouldn't be crazy surprising. We know that cosine x has that perfect symmetry we call even symmetry. It's a reflection across the y-axis. And all of the even polynomials have that same symmetry, x squared, x to the 4, x to the 6. And sine x has odd symmetry. So whatever happens on one side of the y-axis, if you wanted to reflect it diagonally over the origin, you get kind of a mirror image diagonally. That's odd symmetry. And you get that same kind of symmetry out of all of the odd polynomials, x cubed, x to the 5, x to the 7, and so on. In the following table, you can see common Maclaurin series for various different functions. First function is 1 over 1 minus x. It's got a very nice Maclaurin series. This is centered at 0, and it's actually the geometric series. It's just 1 plus x squared plus x cubed. The common ratio of one term to the next is simply just x. And for a geometric series, it's convergent whenever that ratio has an absolute value less than 1. So we say that the radius of convergence is r equal to 1. This is only convergent over the interval from -1 to +1. And we've seen the exponential function e to the x has a very nice Maclaurin series. And we've seen cosine x. Sine x is very similar. These three functions here have a radius of convergence that is infinite, meaning that these power series converge to those functions over all real numbers. We also have some Maclaurin series for arctangent of x and the natural logarithm of 1 plus x. These two functions only have a radius of convergence equal to 1, so they're only convergent from -1 to +1. But we can still get a nice polynomial representation of arctangent as well as the natural logarithmic function. Now, a big use for these power series representations is so we can do some interesting calculus on functions that may otherwise be very difficult to integrate. For instance, trying to look for the antiderivative or the indefinite integral of e to the x squared isn't really that trivial. It kind of looks like you should be able to do a substitution, but unfortunately you can't, and it's not one that we can easily represent as a result as a function. But we can take a look at its power series representation and see what integrating that would do. Let's take a look at e to the x squared. We already know that e to the x is the power series from n equals 0 to infinity of x to the n over n factorial. Well, if we want e to the x squared, we simply have to replace all of the x's with x squareds on both sides of this equation. Well, x squared to the n over n factorial can be simplified to be x to the 2n over n factorial. Starting at n equals 0, this gives 1 plus x squared plus x to the 4 over 2 factorial plus x to the 6 over 6 factorial, and so on. And because the radius of convergence of our power series representation of e to the x was infinite, then that would also imply that by a little change of x to x squared, we still have an infinite radius of convergence. And now, if we want to take a look at this impossible integral, the indefinite integral of e to the x squared dx, we know that we can't really get that integration completed just by simple methods of integration, but we can integrate its power series instead. Now, at this point in time, we have to remember that this sigma notation just represents a large sum of infinitely many terms. And if we apply the integration operator to a sum of multiple terms, then we can integrate each individual term on its own. That will allow us to change the order of these two operations. It's at this point in time that we can integrate each term and then apply the sigma notation and sum up all the terms. And since n isn't our variable that we're integrating with respect to, that's just a constant. And we can see that the antiderivative of x to the 2n is now just a simple power rule on each of the terms. This gives us a new power series representation of the antiderivative of e to the x squared. We can definitely say that it's an integrable function. The problem with this is that we can only represent that antiderivative as this power series representation. And we can't seem to find a way to represent the antiderivative of e to the x squared in terms of a finite number of elementary functions. But there's one of our big applications of power series, and in this case, Maclaurin series. There you go. You kind of have this interesting result that comes from all we learn about series, as well as what we've learned about integration and derivatives. Any one of these power series that we have, you can integrate, you can differentiate them, and you can come up with a power series representation of another function. Or if you wish, you can just take something like the power series representation of e to the x and replace the x's with x squareds and come up with a brand new power series representation. You do have to double check and make sure that that radius of convergence isn't affected. But that kind of concludes what we're really looking at here in this video for Taylor and Maclaurin series. There's lots more that we could talk about with sort of the applications of series and power series in particular, but we'll save that for the future. Thanks for watching, and I'll see you in the next video.